EN-US. Friends, today we're going to discuss the most incredible discoveries in space and astronomy that you might have missed. Let's dive right in. In the distant reaches of our vast solar system, a great mystery remains hidden: the possible existence of a ninth planet whose presence is strongly suggested by the unusual orbits of distant celestial bodies. This mysterious cosmic world, dubbed Planet 9, consistently draws the keen attention of astronomers, sparking lively discussions and intense scientific investigations. But what exactly makes these orbits so unusual? The main point is that trans-Neptunian objects move along trajectories that are too peculiar to be fully explained solely by the influence of already known planets. Their orbits imply the presence and influence of a massive, yet unseen force, likely belonging to a planet cleverly concealed in the boundless darkness beyond Neptune. The discovery of Sedna, a cosmic object with an extraordinarily elongated orbit, first hinted at the possible existence of this hidden world. Sedna's journey through the outer reaches of the solar system defies simple explanation by Neptune's gravitational influence alone, leading scientists to suspect the presence of a previously unknown planet. Recent research has significantly intensified this fascinating search, leading to the discovery of more Sedna-like objects, now known as sednoids, and an ever-growing list of extreme trans-Neptunian objects, or ETNOs. Recent work by the distinguished scientist Konstantin Batygin has introduced entirely new ideas, successfully identifying a statistically significant set of trans-Neptunian objects. As researchers delve deeper into these remote regions, compelling evidence is steadily accumulating, suggesting that Planet 9, if it truly exists, could be several times more massive than Earth, orbiting at a distance more than 13 times greater than Pluto's distance from the Sun. Computer modeling, which accounts for the hypothetical influence of Planet 9, shows a striking match with actually observed data, significantly strengthening the hidden planet hypothesis. This text will delve into the origins of the Planet 9 hypothesis, recent research, and alternative theories that force us to rethink our established understanding of the so-called backyard of the solar system. The search for Planet 9 began with a series of observations that truly puzzled astronomers: the unusual orbits of distant objects located in the outer solar system, far beyond Neptune. These objects, known as trans-Neptunian objects or TNOs, moved along trajectories that could not be explained by the gravitational pull of known planets alone. In the early 2000s, astronomers noticed that some trans-Neptunian objects had very strange, highly elongated orbits. One such object, Sedna, discovered in 2003, became a key piece of this grand celestial puzzle. Sedna's orbit extends an astonishing 937 astronomical units from the Sun, far beyond Neptune's sphere of influence. The discovery of Sedna posed a crucial question to scientists: what exactly could have caused such an extreme orbit? Even the gravitational influence of Neptune alone was insufficient to comprehensively explain Sedna's trajectory, suggesting the possible presence of some other massive cosmic object. In 2016, astronomers Michael Brown and Konstantin Batygin put forth an innovative hypothesis. They proposed that a ninth planet, significantly larger than Earth, could be gravitationally influencing these distant objects, thus shaping their orbits. Their research convincingly showed that the orbits of several trans-Neptunian objects are clustered in a way that clearly points to the gravitational pull of a massive yet unseen planet. This clustering, where orbits align in a specific direction, cannot be simply explained by the known dynamic laws of the solar system. The discovery of Sedna and the subsequent identification of similar objects, now classified as sednoids, further support this hypothesis. Sednoids, like Sedna, possess orbits that clearly indicate the gravitational pull of some distant, massive body. Brown and Batygin's work sparked a surge of new interest in studying the outer regions of the solar system. Their computer modeling showed that Planet 9 could be 10 times the mass of Earth and orbit the Sun at a distance of 400 to 800 astronomical units. As the active search for Planet 9 continues, the hypothesis has also steadily evolved, incorporating new discoveries and significantly improved models. Recent research has significantly strengthened the theory of a ninth planet's existence through the application of advanced statistical methods and new observational data. A recent scientific paper by Konstantin Batygin and his colleagues identified a statistically significant set of trans-Neptunian objects whose peculiar orbits are best explained by the presence of Planet 9. The study is based on a comprehensive approach known as N-body modeling, which carefully simulates the gravitational perturbations emanating from all giant planets, as well as from galactic tides and passing stars. This detailed approach demonstrates that the observed orbital architecture of some trans-Neptunian objects, or TNOs, remarkably aligns with predictions made by models that include the presence of Planet 9. One of the most significant achievements of this research is the 5 sigma level of certainty achieved in the statistical analysis. In scientific terms, this means that the probability of the obtained data being the result of pure chance is only 1 in 3.5 million. Such a high level of confidence substantially strengthens the arguments for the hypothetical existence of Planet 9. The modeling convincingly shows that without the presence of Planet 9, the distribution of these objects in perihelion rapidly decreases as they approach Neptune's orbit, forming a powerful dynamic barrier. Conversely, when Planet 9 is included in the model, the distribution flattens, directly indicating its constant gravitational influence and modification of object orbits. An intriguing addition to the family of trans-Neptunian objects is the recently discovered extreme trans-Neptunian object known by the complex name Lele Akuhonua. The orbit of this ETNO is highly elongated, reaching distances significantly beyond Neptune's orbit. Its discovery provides additional, very strong evidence of the gravitational influence of a distant massive object, such as Planet 9. Further analysis involves the clustering of orbital elements, such as perihelion and semi-major axis, which consistently align in models that include Planet 9. This clustering is statistically significant and provides compelling evidence for the existence of a massive distant planet. Planet 9, if its existence is confirmed, is hypothetically a massive celestial body whose orbit extends far beyond Neptune. Theoretical models presented in this study suggest that Planet 9 could possess a mass 5 times that of Earth and orbit the Sun at a distance of approximately 500 astronomical units with moderate eccentricity and a certain inclination. This distant orbit implies a significant gravitational impact on trans-Neptunian objects, especially those that cross Neptune's path. Planet 9's gravitational influence can create diverse orbital patterns among these objects. To comprehensively understand these effects, researchers conducted extensive N-body simulations, integrating the orbits of thousands of trans-Neptunian objects over billions of years. These models had to account for the gravitational influence of the Sun and all major planets, perturbations from galactic tides, including the Milky Way's gravitational field, and the influence of passing stars, which can alter TNO orbits over time. Each simulation underwent multiple iterations to ensure reliability and accuracy, minimizing the impact of any single anomalous result. Ultimately, the results obtained show striking differences between simulations with and without Planet 9. Simulations including Planet 9 show that trans-Neptunian objects exhibit a wider range of perihelion distances and more stable clustered orbits. In contrast, models without Planet 9 do not reproduce the observed clustering, strongly indicating the necessity of its gravitational presence. To ensure accuracy, the study also considered potential observational errors. Researchers adjusted for errors related to detecting objects with large inclinations and at large heliocentric distances. By weighting the observed data to account for these errors, they ensured that the simulation results were robust and consistent with reality. An intriguing aspect of Planet 9's influence is its ability to trigger the Litov-Kozai mechanism, a gravitational effect that causes trans-Neptunian objects to oscillate between high and low inclination as their eccentricity increases. This mechanism could explain the highly inclined Neptune-crossing orbits observed in the outer solar system. Simulations show that Planet 9's gravitational pull can induce these oscillations, leading to the unique orbital patterns we observe today. However, despite all efforts, the detection of Planet 9 faces colossal observational challenges due to its significant distance and extremely low luminosity. Current search strategies involve conducting deep sky surveys using powerful telescopes capable of registering faint objects at vast distances. Future space missions, particularly those carried out by the Vera C. Rubin Observatory, are expected to provide significantly more comprehensive and detailed data, thereby increasing the chances of detecting Planet 9. These advanced observatories will systematically scan vast areas of the sky, improving our ability to identify distant objects and refine Planet 9's predicted location. As humanity continues to refine its theoretical models and observational techniques, the mystery of Planet 9 remains one of the most captivating frontiers in astronomy. The combination of complex theoretical modeling, detailed computer simulations, and advanced observational strategies is steadily bringing us closer to unraveling the mystery of this elusive cosmic giant. In exploring the uncharted depths of the outer solar system, one of the most compelling alternatives to the Planet 9 hypothesis is the suggestion of a primordial black hole's existence. These hypothetical black holes are believed to have formed in the earliest stages of the universe, long before stars and galaxies emerged. A primordial black hole could possess a mass comparable to the estimated mass of the hypothetical ninth planet, but its size would be significantly smaller, making its detection by traditional optical telescopes extremely difficult. Its powerful gravitational pull could well explain the observed clustering of trans-Neptunian objects. While this hypothesis is intriguing, it faces certain difficulties. A black hole's gravitational influence would likely cause more extreme dynamic effects on nearby objects, and additional phenomena, such as gravitational lensing, which have not yet been detected, would be expected. Despite the very strong evidence suggesting the existence of Planet 9, some astronomers have put forward counter-arguments challenging this hypothesis. One key argument is the possibility that the observed orbital clustering of trans-Neptunian objects could be the result of observational bias or systematic distortion. Researchers suggest that the limited sky regions covered by deep surveys may create a false impression of clustering. As more objects are discovered and cataloged, the clustering effect may significantly diminish, completely eliminating the need for a massive unseen planet. Another alternative explanation involves the Oort cloud, a vast spherical shell composed of icy objects surrounding our solar system at its outermost reaches. The mass and spatial structure of the Oort cloud could play a significant role in shaping the orbits of objects beyond the main part of our system. If the Oort cloud contains significantly more mass than previously assumed, its gravitational influence could affect the orbital dynamics of trans-Neptunian objects, naturally leading to the observed clustering and eccentricities. In turn, galactic tides and the gravitational forces exerted by the Milky Way on our solar system represent another important factor in this complex cosmic puzzle. These tides can influence the orbits of distant objects over long periods. Research shows that such tidal forces can perturb the orbits of trans-Neptunian objects, contributing to the observed clustering. The combined action of galactic tides and the gravitational influence of a more massive Oort cloud could potentially explain the unusual orbits without the need to introduce the hypothesis of a ninth planet. When evaluating these alternative theories, each presents unique challenges and consequences for our understanding of the outer solar system. The true nature of the observed gravitational effect remains a subject of active scientific research and lively debate. The search for Planet 9 is a priority for many astronomical studies and observatories worldwide. Among the most prominent projects is the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope. This advanced astronomical complex is designed to systematically survey the entire sky, collecting vast amounts of data with unprecedented detail. The observatory's wide-field imaging system will be capable of detecting faint objects far beyond Pluto's orbit, significantly increasing the likelihood of identifying Planet 9 or another similar distant celestial body. Future missions, such as the Nancy Grace Roman Space Telescope, are expected to play a crucial role in this search. This next-generation telescope will have higher resolution, greater sensitivity, and allow astronomers to look deeper into the outer solar system. It will complement ground-based observatories by providing detailed observations of candidate objects, helping to confirm their nature and refine their orbits. The discovery of Planet 9 would significantly alter our understanding of the solar system's architecture. It would redefine the boundaries of our planetary system, extending it far beyond the known planets, and provide new data on its formation and evolution. Such a discovery would challenge existing models of solar system dynamics and require a revision of our theories of planet formation and migration. The existence of a distant, massive planet in our solar system could have profound implications for exoplanet studies. It suggests that planetary systems may contain distant, massive objects that influence the orbits and stability of other planets within those systems. A prime example is an exoplanet in the Southern Cross constellation system, an 11-Jupiter-mass planet with a highly eccentric orbit around its star, located approximately 336 light-years from Earth. This planet's orbit is significantly inclined and elongated, resembling the hypothetical orbit of Planet 9. Its study provides valuable insights into how massive and distant planets can influence the architecture of their planetary systems, potentially offering clues to the formation and dynamics of Planet 9. This comparison will help astronomers better understand the diversity and formation of planetary systems across the galaxy. By pushing the boundaries of research, astronomers aim to unlock the mysteries of the distant regions of our solar system, paving the way for future discoveries and technological advancements. This path of discovery is not only about unraveling the secrets of our solar system, but also about expanding our understanding of the universe beyond it. Whether it's a hidden planet, a primordial black hole, or something entirely unexpected, one thing is certain. Every step forward only brings us closer to understanding the profound mysteries of the cosmos. In the universe, there are places where the laws of physics, as we know them, teeter on the brink of oblivion, where time warps and space bends. Centuries ago, an apple fell, and with it, the seeds of Sir Isaac Newton's gravitational theory were sown. It was a simple truth, an apple drawn to Earth. Yet it unveiled a cosmic meaning that binds the universe together. However, within this meaning lies a colossal breach, so potent that no known particle can escape it. This is the realm of black holes, cosmic enigmas that have baffled astronomers, physicists, and philosophers for decades. Imagine, if you will, a whirlpool in the fabric of space-time, so powerful that even light cannot resist its pull. This is the event horizon, the point of no return. It is here, at the very heart of this cosmic anomaly, that the concept of singularity resides, a point where mass is believed to be compressed to infinite density, and the laws of physics crumble under the weight of its impossibility. But what if everything we once thought about these dark giants is only part of the truth? What if the singularity, this point of infinite density and zero volume, is not the inevitable end of a black hole's center? Recent research has begun to pull back the curtain on this mysterious phenomenon, questioning the very concept of singularity and proposing a reality far more complex and even more enigmatic. In the heart of the 20th century, as physicists delved deeper into the fabric of the cosmos, a groundbreaking theorem emerged, solidifying its place in the annals of physics. Sir Roger Penrose, a visionary British physicist, introduced the Penrose singularity theorem to the world, challenging our understanding of the universe and its most enigmatic entities, black holes. This theorem, presented in 1965, leverages the mathematical foundations of general relativity to make a profound statement about the nature of black holes and the inevitability of singularities within them. Penrose's theorem is based on a fundamental principle of Einstein's general relativity, which treats gravity not as a traditional force, but as a curvature of the space-time continuum generated by mass and energy. According to this theory, massive celestial bodies, such as stars and planets, warp the fabric of space-time around them, influencing the movement of objects and even the path of light rays. The singularity theorem, proposed by Penrose, states that under certain rational conditions, particularly the presence of a trapped surface, where light rays converge rather than diverge, a singularity must form inside a black hole, a region of infinite space-time curvature. This trapped surface marks the point of no return, beyond which all trajectories inexorably lead to the singularity, a place where the commonly known laws of physics cease to apply. One of the most significant implications of Penrose's theorem is the idea of geodesic incompleteness in the context of spacetime. A geodesic represents the shortest path between 2 points, analogous to a straight line in curved space. Penrose's theorem implies that inside a black hole, some of these geodesics cannot be infinitely extended either into the past or into the future, indicating the existence of a boundary of spacetime itself, the singularity. Imagine you're kayaking down a serene, wide river that symbolizes the universe. The current of this river, its continuous flow and direction, reflect the paths in spacetime, known as geodesics, along which planets, stars, and light travel under the influence of gravity. As you progress, you approach an area where the river's current becomes increasingly turbulent and restless. Ahead, a massive, hidden waterfall awaits, shrouded in dense fog. This waterfall can be compared to a black hole, and the point where the water masses begin to plunge rapidly downward resembles the event horizon, the boundary beyond which there is no return. As the water approaches the waterfall, currents that previously flowed parallel begin to converge and accelerate towards the edge of the cliff. Despite the speed of the water and the power of the river, nothing can escape the waterfall's pull once it reaches the edge. This convergence of river currents at a single point, which never reaches a stable conclusion, illustrates the concept of geodesic incompleteness near a singularity inside a black hole. Near the event horizon, a photon kayak trying to paddle directly against the current simply stays in place no matter how much effort you exert. But you can never paddle away from there. The internal currents of space completely nullify your movement. Inside the event horizon, the cosmic waterfall sweeps everything away at a speed exceeding the speed of light. The water, symbolizing the paths of particles, does not simply stop or compress. Rather, the very nature of the riverine space, the entire landscape, changes dramatically at the waterfall. The paths of the water are forced to converge and plunge due to the structure of the waterfall, similar to how space-time around a black hole is so dramatically curved that all paths are inexorably drawn towards the singularity. The implications of Penrose's work were profound. If singularities truly exist within black holes, then general relativity, our best theory of gravity and the large-scale structure of the universe, is fundamentally at odds with quantum mechanics, the theory governing the subatomic world. This conflict, known as the problem of quantum gravity, remains one of the most significant challenges in modern physics. In 2020, the Nobel Prize in Physics was awarded to Roger Penrose for his discovery that black hole formation is a robust prediction of general relativity. The award not only recognized Penrose's pioneering work, but also highlighted the critical role of singularities and the deep, unresolved contradictions between the pillars of modern physics, namely, the reconciliation of the colossal scale of the cosmos with the infinitesimally small quantum world. In the annals of black hole theory, one name stands out that significantly expanded our understanding of these cosmic enigmas: Roy Kerr. This New Zealand mathematician proposed a revolutionary perspective that forever changed the landscape of astrophysics. Kerr's groundbreaking contribution was the Kerr metric, a solution to Einstein's equations of general relativity describing the spacetime surrounding a rotating black hole. Unlike the static, non-rotating black holes represented by Schwarzschild, Kerr black holes were living, rotating entities, reflecting the dynamic, spinning universe we observe. We observe astonishing phenomena, and one of the most remarkable results of Kerr's research on rotating black holes was the discovery of the ergosphere. This unique region is located immediately outside the event horizon, where the black hole's intense rotation causes space-time itself to deform, dragging everything within it along. In this part of the cosmos, the very matter of the universe seems to waltz in unison with the colossal rotation of the black hole, challenging familiar human notions of space and movement. Within the ergosphere, physical laws manifest in a very unusual and captivating way. Here, elementary particles and quanta of light can accelerate to incredibly high speeds, drawing kinetic energy directly from the black hole's rotation. This astonishing phenomenon stimulates the imagination, opening up, albeit purely theoretically, the prospect of harnessing black hole energy, an idea that was once considered exclusively the domain of science fiction literature. Perhaps the most radical aspect of Kerr's work was his groundbreaking reinterpretation of the nature of singularity itself. The traditional concept of a point singularity, representing a point of infinite density at the very heart of a black hole, was abolished. Instead, Kerr put forward the idea of a ring singularity, a closed loop of unimaginable density and gravitational pull, a concept that significantly expands the horizons of mathematical understanding. Such an interpretation was not merely an outstanding mathematical achievement. It marked a fundamental shift in understanding the dynamics of the universe. Black holes, as described by Kerr, actively rotate, obeying the same universal forces that drive planets around stars, stars themselves, and entire galaxies. At the heart of this complex scientific challenge lies a profound understanding of the trajectories along which elementary particles and light geodesics travel through deformed spacetime in the vicinity of black holes. For a long time, the prevailing view was that these paths, both null geodesics describing the movement of light and the trajectories of material objects, inevitably terminate in a singularity, that is, a point of infinite density where the physical laws we know cease to apply. However, recent research has presented a fundamentally new, revolutionary perspective. Kerr insisted that the concept of geodesic incompleteness, the idea that paths in spacetime must end in a singularity inside a black hole, stems from a misinterpretation. He argued that, despite the possible limitations of the mathematical parameters that describe these trajectories, this does not necessarily imply the mandatory collapse of space-time itself into a singularity. According to Kerr, the paths of light rays inside a black hole, obeying null geodesics, could indeed be confined by the event horizon of this cosmic object. However, such a boundary would not signify the end of spacetime's existence or the inevitable presence of a singularity. Instead, Kerr hypothesized that these closed trajectories could exist within the complex internal architecture of a black hole, without requiring the existence of a singular point of infinite density. Furthermore, the Kerr metric introduced the concept of an event shell, which differs from the event horizon, and suggested that trajectories within this shell depend on fundamental characteristics such as the black hole's angular momentum and mass, opening up the possibility for a whole spectrum of behaviors that had not been considered until then. Central to this study is the striking contrast between a Schwarzschild black hole, defined by its point singularity, and a Kerr black hole with its enigmatic ring singularity. This ring, arising as a consequence of the black hole's rotation, distributes the singularity along its axis, forming a structure significantly more intricate than the single singular point proposed by Schwarzschild. The ring singularity of a Kerr black hole opens up a kaleidoscope of potential scenarios for researchers, where the trajectories of light and matter are not doomed to a fatal termination in a singularity, but can bend and spiral around this colossal gravitational vortex. This extraordinary structure allows, in theory, for the possibility of paths passing through the ring, which may indicate a kind of portal to other regions of spacetime, or the emergence of completely unforeseen cosmic phenomena. As a Kerr black hole rotates, it actively drags space-time along with it, capturing the very fundamental fabric of the cosmic continuum. This phenomenon, known as frame dragging, leads to a significant distortion of the trajectories of light and material objects, forcing them to spiral around the black hole. This phenomenon sharply contrasts with the rectilinear fall to a singularity predicted in models of non-rotating black holes. In this grand maelstrom of deformed spacetime, theoretical concepts predict the emergence of such unusual and exotic phenomena as closed time-like curves, hypothetical paths that, according to theory, can return to their own past, thereby challenging our usual understanding of time and the principles of causality. Observations related to Kerr black holes present a significant challenge to Penrose's generally accepted theorem. If these unique astrophysical objects, characterized by the absence of a singularity in their principal null vectors, turn out to be not just a mathematical abstraction, but a real and integral part of our universe, then the universality of Penrose's theorem is seriously called into question. The fact that trajectories exist within black holes that allow for the avoidance of singularity indicates a much more complex nature of reality than simply the concept of a point of no return. This circumstance urgently requires a revision of existing theoretical models. Amidst this revision, the search for a unified theory of quantum gravity, a comprehensive concept capable of organically uniting the quantum world with the cosmic, linking its infinitesimally small scales with the unimaginably vast, does not diminish. And there is every reason to hope that theoretical physicists can now experience some relief, not being so rigidly constrained by the conventions dictated by space-time singularity. Imagine standing on the edge of a boundless expanse of water, reflecting the shimmering abyss of the cosmos. Now imagine that this majestic panorama, with all its countless stars and swirling galaxies, is merely a reflection, a projection emanating from an unseen distant shore. This is not the premise of a science fiction novel, but rather a profound dive into one of the most astonishing and intriguing theories of modern physics, the holographic principle. Just as every tiny dewdrop on a spiderweb can encapsulate an entire world in miniature, so too may our vast universe be a grand reflection of fundamental laws inscribed on some distant boundary. Far from the solid ground beneath our feet and the bottomless void of outer space, the very fabric of our reality may be generated by something far deeper and more fundamental than what is accessible to our current understanding. At the heart of physical research lies a relentless quest, a drive to unveil the layers of reality, to identify its most fundamental components. These elements, known as ontological primitives, represent the bedrock upon which the grand edifice of the universe is built. For centuries, physicists have diligently sought these building blocks, striving to grasp the rules that govern their intricate interactions. This journey begins with an understanding of the concept of space. Isaac Newton, one of the greatest thinkers in the history of science, envisioned space as an absolute, immutable backdrop that remained indifferent to the emergence and disappearance of matter and energy. For Newton, space was an absolute container, an infinite volume in which all events of the universe unfolded. However, as our understanding deepened, this view of space began to transform. The advent of Albert Einstein's theory of relativity presented an entirely different picture, where space ceased to be merely a passive stage, transforming into an active participant in cosmic interaction. According to this new view, space could curve and deform in the presence of mass and energy, challenging the very idea of its absolute nature. Amidst these shifting perspectives, a radical idea arises: the holographic principle. This principle suggests that our three-dimensional perception of the universe may be akin to a hologram, a projection emanating from a two-dimensional surface located at the very boundary of space. This boundary, though infinitely distant and inaccessible to direct observation, may contain the fundamental information that gives rise to everything we perceive as reality. This concept overturns our usual notions, asserting that the very essence of space, the fabric of our reality, may not be a fundamental characteristic of the universe, but rather an emergent one. Emergentism describes phenomena that arise from the complex interaction of simpler elements, leading to the appearance of new properties and behaviors that are not evident from the components alone. In the context of our universe, and especially within the holographic principle, emergentism plays a truly fascinating role. Here, the term implies that the three-dimensional space in which we move and the time we experience are not fundamental building blocks of reality. Instead, they emerge from a more basic or two-dimensional structure, the holographic boundary that encodes the information and laws that generate our perceived reality. Within this concept, every star, every planet, and every galaxy, every law of physics, from gravity to electromagnetism, and the very fabric of the cosmos are emergent phenomena. It is a kind of bridge between the known and the unknown, between the observed dimensions of our universe and the fundamental encoding of reality on the holographic boundary. This idea prompts us to rethink not only the structure of the cosmos, but also the very nature of reality, as we gradually peel back the layers of the universe, one by one. Against the backdrop of our hypothesis, black holes, where gravitational force triumphs to such an extent that even photons of light cannot escape its all-consuming pull, unexpectedly became central figures thanks to the groundbreaking ideas of Stephen Hawking and Jacob Bekenstein. These eminent scientists dared to venture into uncharted territory, seeking to unite the fundamental fields of quantum mechanics and general relativity to deeply investigate the thermodynamic properties of black holes. Their revolutionary theories revealed a startling fact. Black holes are not absolute endpoints of entropy, but rather key participants in the grand cosmic interplay of information and energy. Entropy, traditionally associated with disorder or chaos in a system, acquired an entirely new dimension in their hands. It became a kind of veil, concealing a colossal amount of information within black holes. This was not merely about a random distribution or chaotic movement of particles, but about layered, hidden information that, in essence, defines the very structure and essence of reality. As matter rapidly spirals into a black hole, it seemingly disappears irrevocably from our universe, raising an extremely important question. What happens to the information it carries? This question draws attention to entropy, not merely as a quantitative measure of disorder, but as a crucial key to a deep understanding of the fate of absorbed information. Black hole entropy, as proposed by Bekenstein, is directly proportional to its surface area, not its volume, a concept that radically contradicts our everyday intuitive understanding of physical laws. This astonishing connection between surface area and entropy leads us to a profound conclusion. The maximum amount of information that can be contained in any given region of space is determined not by its volume, as one might intuitively assume, but by its surface area. This fundamental perspective laid a solid foundation for the so-called holographic principle, which suggests that all information about a certain volume of space can, in principle, be effectively encoded on a two-dimensional surface surrounding that volume. Thus, the revolutionary discoveries of Hawking and Bekenstein in the thermodynamics of black holes suggest the existence of a cosmos in which the very fabric of reality, literally every elementary particle, every fundamental force, and the very dimensions of space and time, may be merely emergent properties arising from a deeper fundamental two-dimensional fabric. At the forefront of bridging the gap between the mysteries of black hole thermodynamics and the holographic principle is the distinguished physicist Juan Maldacena. His work represents not just a theoretical framework, but a concrete, highly compelling example of holographic principles in action. Maldacena's correspondence asserts a fundamental duality between a certain type of space known as anti-de Sitter (ADS) space and a conformal field theory (CFT) that exists on the boundary of that space. Despite our universe's positive cosmological constant, which sharply contrasts with ADS space's negative constant, the principles derived from this duality offer invaluable insights into the nature of gravity and quantum mechanics, and, in essence, the holographic nature of our universe. Central to this duality is the conformal field theory, which operates at the boundaries of the universe within the ADS-CFT correspondence. CFT is unique in its scale invariance. The laws governing these field theories remain unchanged regardless of the size or scale at which they are observed. This fundamental property of CFT is key, as it encodes the information necessary to describe the bulk space of higher dimensions within lower dimensions, effectively illustrating the holographic principle. Scale invariance in CFT is not just a mathematical curiosity, it is a profound window into the emergence of dimensions and the very fabric of space. Different scales of patterns on the boundary, governed by the uniform laws of CFT, contribute to the illusion of three-dimensional space. This phenomenon vividly highlights the holographic principle. The complexity and dimensions of bulk space arise from simpler, scale-invariant dynamics on the boundary. Through the lens of ADS-CFT correspondence and the subtleties of conformal field theory, we gain a deeper understanding of how dimensions and the very structure of spacetime can emerge, with scale-invariant boundary patterns each contributing to the holographic encoding of the universe. One of the most vivid and understandable metaphors to grasp this multifaceted concept is the idea of nested spheres. These spheres, nested one within another, form a visual basis where each subsequent layer embodies different scales of boundary patterns. The smallest, barely perceptible patterns, akin to microscopic elements, are extremely densely packed with information, requiring high resolution and close attention for their comprehension. As we move to consider larger spheres, these patterns take on a coarser character, while still retaining the same information, but in a more generalized and less detailed form. In the smallest space of the holographic boundary, patterns possess high density and exceptional detail, resembling the finest brushstrokes of a distinguished artist. These fine-grained patterns are the primordial basis for the entire universe, where every microscopic element is literally filled with information, encoding the fundamental laws of physics and the initial conditions of cosmic phenomena. The transition from microscopic to macroscopic environments is like closely examining a mosaic. At first, we distinguish only individual tiles, each with its unique color and shape. But as we move away from it, a complex and harmonious whole image appears before us. Similarly, the majestic structure of the universe, galaxies, stars, and planets, arises from the collective interaction of these fundamental patterns encoded on the holographic boundary. This gradual transition from fine-grained to coarse-grained patterns observed at the universe's boundary is not merely a characteristic feature of the holographic model. It is a fundamental process that actively shapes our perception of space. It vividly demonstrates the differences and specific information requirements at various scales, highlighting the remarkable adaptability and high efficiency of holographic encoding of spatial reality. The concept of a holographic universe rests on a profound philosophical and scientifically grounded notion called ontological democracy. This idea implies that the boundaries of the universe, with their two-dimensional way of encoding information, and the three-dimensional space with which we interact daily, may possess equal fundamentalness to the very fabric of reality. Neither of these manifestations is more true or primary than the other. Rather, they exist in a state of mutual emergence and are inseparable from each other. Such a perspective carries far-reaching consequences. It suggests that what we perceive as a three-dimensional reality, consisting of stars, galaxies, and planets, with all their complex and diverse interactions, may represent only a manifestation of deeper, more fundamental laws that are encoded on a distant and invisible boundary. And this encoding not only determines the structure of the volume, but is also shaped by events occurring within it, thus creating a continuous feedback loop. In our journey through the holographic universe, we encounter a profound re-evaluation of the nature of gravity, traditionally perceived as the curvature of spacetime under the influence of mass. Within the holographic concept, gravity arises not from mass itself, but from the entropic forces acting within the information encoded on the boundary of the universe. Now, the idea that gravity can be an emergent phenomenon, similar to temperature or pressure in thermodynamics, represents a truly radical shift in the established perspective. It suggests that what we perceive as gravitational attraction is the result of the universe's inherent tendency to maximize entropy, a thought first put forward by the distinguished physicist Eric Verlinde. This theory posits that gravitational attraction arises from changes in the amount of information associated with the positions of material objects. The holographic universe also urges us to carefully investigate the mysterious role of quantum entanglement in the very fabric of space-time. Quantum entanglement, a phenomenon in which particles remain interconnected in such a way that the state of one particle can instantly influence the state of another, completely independently of the distance separating them, is perhaps the invisible thread that weaves this spatial continuum of the universe. According to this view, space itself arises from the entanglement of quantum bits encoded on the cosmic boundary. When particles are entangled, they share a common, unbreakable bond that contributes to the illusion of continuous space. Theoretically, disentangling these particles could lead to the complete disappearance of space between them, challenging the very notion of distance and locality in our universe. The idea of a holographic universe, like many other profound concepts in physics, inevitably leads to one key question: the need to find a universal holographic model. This grand endeavor aims to unite the countless complexities of the universe into one cohesive structure, capable of describing with astonishing accuracy both the vast cosmic scales and the minutest nuances of quantum mechanics. The obstacles on this path are truly colossal. Creating such a comprehensive model requires not only the deepest understanding of quantum mechanics and general relativity, but also an innovative approach to integrating these fundamental theories into a unified holographic construct. The potential discoveries promise to completely overturn our understanding of the cosmos. A successful universal holographic model could open unprecedented horizons for understanding the origin of the universe, the nature of black holes, and the fundamental laws governing reality itself. As we journey through the labyrinth of possibilities and limitations of this theory, we may find ourselves on the threshold of a new era of cosmic understanding, or witness another refutation of a grand hypothesis. If reality is indeed holographic, then our perception, our life experience, and our very existence may be much more intimately intertwined with cosmic space than we could ever have imagined. This path is full of difficulties and the unknown, but the promise of unraveling the deepest mysteries of the universe steadily drives us forward in pursuit of the elusive universal model that could redefine our place in the infinite cosmos. In the serene and almost palpable silence of boundless outer space, a discovery recently emerged that immediately raises countless questions. Imagine a region of the cosmos where the very fundamental laws of physics seem to have been rewritten, where a recorded celestial anomaly unequivocally points to the existence of a true cosmic giant, a black hole named Gaia BH3. Black holes have for centuries invariably attracted the inquisitive curiosity of both astrophysicists and the general public. These mysterious objects of the universe possess such a colossal gravitational pull that even photons of light cannot escape their bottomless embrace. Deeply rooted in the very fabric of space-time, they exert an influence on their surroundings that, though seemingly subtle, is in fact profound and all-encompassing. However, how can such a significant discovery affect our own civilization? Located just 2,000 light-years away, can this silent cosmic neighbor have any tangible impact on our solar system? Or does its presence merely expand the already enormous circle of cosmic mysteries that surround us on all sides? Thus, it is well known that in the depths of the universe, black holes possess such a powerful gravitational pull that it warps the very fabric of space-time. These cosmic phenomena, shrouded in many mysteries, are not merely abstract points in space, but rather dynamic and active regions where the force of gravity reaches such intensity that the usual laws of physics struggle to remain applicable. However, to understand the nature of these amazing celestial phenomena more deeply, it is necessary to consider them in more detail. The gravitational power of a black hole is truly colossal. It is this property that causes the warping of space-time around it, and consequently the capture of even light. Nevertheless, despite all its grandeur, its influence has its spatial limitations, dictated by the immense scales of the cosmos. The widespread notion that a black hole can wander aimlessly through cosmic space, devouring stars and entire galaxies in its path, is a profound misconception. This myth is generally actively cultivated, not by rigorous science, but rather by sensational reports and cinematic works of fiction. In reality, the gravitational influence of black holes does not extend infinitely far. On the contrary, their influence rapidly diminishes with increasing distance from them. Consequently, even those black holes that are relatively close to our solar system, such as Gaia BH3, pose no direct and immediate threat to the existence of our planet and the entire system as a whole. To deeply grasp this issue, we must once again turn to the pages of history, or more precisely, to the narrative of Cygnus X1, the first black hole ever discovered. This story begins not merely with its discovery, but with a very bold wager struck in the world of astrophysics. It was the late 1960s, an era of intense cosmic research and heated scientific debates. Cygnus X1 was first detected as an anomalously powerful source of X-ray radiation by a sounding rocket launched in 1964. This object was not just another luminous point in the night sky, but a source emitting X-rays with an intensity that surpassed virtually all other celestial objects. The intrigue surrounding Cygnus X1 significantly increased when two of the most prominent intellects of the time, Stephen Hawking and Kip Thorne, made the now legendary wager. Thorne argued that Cygnus X1 was a black hole, while Hawking took the opposite stance, hoping to be proven wrong, which was part of his deep desire for a complete understanding of this cosmic phenomenon. This wager became a symbol not only of scientific curiosity, but also of the playful rivalry that often serves as a powerful stimulus for many great scientific discoveries. Cygnus X1 is part of an X-ray binary system that includes a blue supergiant star and an object now believed to be a stellar mass black hole. The black hole's powerful gravitational field pulls matter from its stellar companion, which, spiraling into the black hole, heats up to millions of degrees Celsius and emits X-rays. These emissions allowed astronomers, using instruments like the Uhuru satellite, launched in 1970, which became the first satellite specifically designed to study X-ray sources, to investigate the characteristics of this mysterious object in more detail. The Uhuru satellite, as the first space telescope, provided undeniable evidence that this object was indeed a black hole, and the first of its kind. Cygnus X1 significantly enriched our knowledge of the nature and behavior of black holes, particularly how they interact with surrounding matter. It serves as a crucial reference point in the study of Gaia BH3. Despite Gaia BH3's impressive mass of a staggering 33 solar masses, it remains a silent observer in cosmic space, primarily due to its significant distance from a star capable of supplying material for an accretion disk. This distance implies the absence of significant X-ray emissions and a quiet, calm existence, which sharply contrasts with the dynamic and active environment around Cygnus X1. While Cygnus X1 is approximately 7,000 light-years from Earth, Gaia BH3 is closer, about 2,000 light-years away. Despite this relative proximity, Gaia BH3's passive nature and our advanced understanding of black hole mechanics give us confidence in its safety. Through the prism of history and advancements in black hole studies, we see that these amazing objects, while possessing colossal power, are limited by the fundamental laws of physics, making fear of them as stellar predators completely unfounded. In the relentless quest to unravel the mysteries of our universe, the Gaia telescope has become a key player in the latest chapter of space exploration. Designed to map stars with unprecedented precision, it introduced a new player to the cosmic arena, the massive black hole Gaia BH3, which is now the closest black hole to us. The mission to map over 1 billion stars has provided a clearer and more detailed view of our galactic neighborhood than ever before. It was during this meticulous survey that the telescope detected an anomaly, a star whose movement could not be explained by ordinary celestial mechanics alone. This star, seemingly invisible, clearly indicated the presence of something massive, hidden from direct observation. And who was the culprit? Gaia BH3, a previously unseen black hole, lurking in the galactic halo approximately 2,000 light-years away. Gaia BH3 is not just another black hole. It's a true cosmic behemoth with a mass of 33 solar masses. This discovery places it among the heaviest stellar mass black holes found in our galaxy. Its location in the galactic halo, a region predominantly populated by older stars and globular clusters, adds intrigue, suggesting a unique origin or evolution compared to black holes found in the galactic disk. One of the most intriguing properties of Gaia BH3 is its absolute silence. Unlike many known black holes that actively betray their presence by consuming surrounding matter and emitting powerful X-rays, Gaia BH3 remains remarkably quiet. The main reason for this silence lies in its solitude. This black hole's companion star orbits it at a significant, safe distance, too far to be tidally disrupted and drawn into the typical accretion spiral that usually forms an accretion disk. Such a large distance prevents significant mass transfer between the stars, and consequently, Gaia BH3 lacks the usual signs of black hole activity, such as powerful jets and intense X-ray emission, which we can observe in other systems, for example, in Cygnus X1. The recent discovery of Gaia BH3 not only adds to our catalog of known black holes, but also provides valuable insights into the mysterious process of black hole formation from low metallicity stars. Low metallicity stars, composed primarily of hydrogen and helium with minimal content of heavier chemical elements, represent an early generation of stars in the universe's history. These cosmic objects, due to their extremely low metal content, experience a deficiency of materials necessary for the process of synthesizing heavy elements, which significantly impacts their life cycle and ultimate demise. The star orbiting Gaia BH3 has been identified as precisely such a low metallicity star, which is a key indicator for understanding its evolutionary path and the nature of its colossal black hole companion. Typically, the fate of a massive star culminates in a grand supernova explosion, which heralds the star's death and the birth of either a neutron star or a black hole. However, for low metallicity stars, the scenario can be significantly different. Reduced opacity due to the absence of heavy elements allows the star to retain most of its mass, leading to the formation of a denser core and its direct collapse into a black hole upon death, without a spectacular supernova explosion. This direct collapse pathway suggests how Gaia BH3's companion could have formed a black hole significantly more massive than those typically formed from more metal-rich progenitors. These direct observational data confirm broader theoretical models in astrophysics, which predict that low metallicity environments favor the formation of larger black holes. These results are of immense significance as they can shed light on the existence of supermassive black holes that appear to have formed very rapidly in the early universe, disproving previous models of black hole growth that required longer timescales and multiple mergers. By studying Gaia BH3 and its stellar companion, astronomers gain invaluable insights into the pre-stellar conditions of the universe, such as times when stars were more common. This discovery not only links past star formation and death processes with phenomena observed today, but also helps fill gaps in our understanding of the distribution and density of black holes in cosmic space. However, science never stands still, and quite recently, thanks to an amazing fusion of artificial intelligence and astrophysics, researchers led by the California Institute of Technology have expanded the boundaries of black hole observations. This team successfully applied advanced artificial intelligence technology to 3D visualize flares that often emanate from such objects, using data from the Atacama Large Millimeter Submillimeter Array, known as ALMA. The team focused its attention on Sagittarius A, the supermassive black hole at the center of our galaxy. They observed flares, bright, energetic emissions that occur several times a day around black holes. These flares, though previously detected, had never been visualized in 3 dimensions until now. To achieve this ambitious goal, the Caltech team developed new computational imaging tools that incorporate AI methods specifically adapted for astrophysical data. These tools were created to address the unique challenges associated with the intense gravitational fields of black holes. A key innovation was the adaptation of a method known as neural radiance fields, or NeRF, originally used to enhance computer graphics. NeRF helps create 3D scenes from 2D images, and this method is ideally suited for astronomical data, which is typically limited to such images. By applying NeRF, researchers were able to simulate how light bends under the immense gravity of a black hole, creating a realistic 3D model of the flare. The team led by Katie Bowman, drawing on a unique set of information obtained using the ALMA radio telescope complex after a powerful eruption near Sagittarius A that was detected in X-rays on April 11, 2017, managed to collect exceptionally important data in the radio frequency range over 100 minutes. This array of information proved crucial for carrying out the fundamental observations necessary for this scientific endeavor. The main task of artificial intelligence was to reconstruct the 3-dimensional trajectory of gas emanating from the black hole, despite the inevitable limitations inherent in observing such cosmic phenomena from Earth. Typically, 3-dimensional observation of celestial bodies requires the use of multiple viewing angles, which is impossible when studying distant black holes. Artificial intelligence successfully filled this gap by simulating these missing perspectives. The team used an advanced version of NeRF technology, specifically adapted for astronomical applications. This modified NeRF system was adjusted to account not only for the bending of light rays caused by the black hole's gravitational field, but also for the expected behavior of the surrounding gas cloud. This innovative method, which can be compared to how a stationary camera captures a rotating object from various perspectives, allowed AI to predict the structural features of the flare over time, based on how the gas would move and how its light would be distorted by the black hole's gravitational lens. The visual data showed the presence of 2 bright objects rotating at a distance of about 75 million kilometers from the black hole's center, which is roughly half the distance between Earth and the Sun. These objects provide a clear representation of the dynamic processes occurring around black holes, and convincingly confirm theoretical predictions regarding their behavior under extreme gravitational influences. The integration of artificial intelligence encompassed not only visualization, but also machine learning, deeply rooted in physical principles. This approach actively uses accumulated knowledge about black hole physics to guide artificial intelligence in reconstructing 3-dimensional structures from the obtained data, taking into account the dynamic movements and transformations of gas in the immediate vicinity of the black hole. This technological breakthrough provides the deepest understanding of the behavior and properties of matter that orbits black holes. Understanding the 3-dimensional structure of these flares helps astrophysicists better grasp how matter behaves in such extreme conditions, including how it moves, heats up, and ultimately accretes onto a black hole. The future of black hole research stands on the threshold of an entirely new era, fueled by the latest scientific discoveries and advanced technological achievements. Methods developed for studying black holes like Sagittarius A and Gaia BH3 provide astronomers with powerful and entirely new tools for detecting and analyzing other black holes that remain hidden or dormant. Such black holes do not actively consume matter, making them incredibly difficult to detect with traditional observational methods that rely on detecting radiation from heated, accreting matter. Furthermore, by mapping the environment of black holes in 3 dimensions, scientists will be able to deeply investigate fundamental questions regarding the nature of their gravity and dynamics. This understanding is crucial for testing the predictions of general relativity and can serve as a basis for future observations and space missions. Beyond this, Each observed black hole provides invaluable data about the history and structure of our galaxy. By studying the properties and behavior of black holes, especially those formed from low metallicity stars or located in unusual parts of the galaxy, such as the halo, astronomers can draw conclusions about the formation and evolution of the Milky Way. This technological breakthrough sets an important precedent for future astronomical observations. By combining artificial intelligence and physics, astronomers can now study other celestial phenomena with unprecedented detail, paving the way for further discoveries and ushering in a new era in the study and understanding of the most mysterious phenomena in the universe. Thanks for watching, friends. See you in the next video.